Everyone here. My name is Max. I'm a member of Extra Muros academic committee. I'm also studying neuroscience, so I'm a bit of a neurogeek myself, but Andrew is going to explain all about that later. Thank you guys for being here. A last lecture is a concept basically that it originates from the United States, where Randy Pausch was also a computer scientist. He was diagnosed with a terminal disease, which caused him to give his last official lecture right at the university that he taught at. And he actually talked not just about his courses, but more of it was intended as a way to give a life lesson to his students. With Extra Muros, we took this concept of the last lecture to invite professors to talk about basically whatever they want to talk about, as long as there's a piece of this wisdom that they've gathered in their lives with. And I'm very excited to welcome Andrew Reid for that today, so please give it up for Andrew.
Okay, thank you very much, Max. Right, last lecture. So interesting concept, and it made me think a little bit. I could have picked a topic of neuroscience and didn't really went into that, but I thought maybe the best idea is to give you an idea of how my career progressed from an undergrad all the way to where I am now. It's unorthodox the way I've come to where I am, and well, maybe not unorthodox. A lot of academics have interesting paths, and I think we maybe don't talk about them as often as we should. So I'm hoping this will give you some insight into what this career trajectory is. I'll give you a little bit of the science I'm doing without too much detail, I hope. Feel free, it's a small group, feel free to stop me with your hand and if you have any pressing questions. Otherwise, I think there's time at the end as well. All right, here's a map of where I have studied in my career. So I'm from Canada here. Does this work? I'm actually from this part of Canada called Newfoundland, but I've lived all over the place and I kind of started over here my career. So I'm going to just show you where it started. First, I went to Waterloo. That's in Ontario. Then, after a year of that, I went to a different university called Memorial University of Newfoundland, a much smaller one. This was also sort of going home trip. Then I made a huge leap. Never having left North America, I decided to go to Germany. And I'll explain how that happened and how I made that decision. That's the big one. So that's over here, number 3. After doing my PhD over here for 4 years, I said, I'm going to go back to Canada. Went all the way back to Montreal, McGill University here. Then I decided to go back. This was a personal reason. I had a girlfriend at the time who was Dutch, and she wanted to go back. And so after much debate, we decided, okay, let's make that happen. So I decided to go back. I ended up in Germany over here, fairly close to where I started. Then I went to the Netherlands. Then I went to England. And finally, I ended up here in Tilburg. So a lot of steps to get where I am. And I'm going to take you through those steps now. Where I started, all the obstacles that I had. Hopefully, you find that interesting. I found it interesting going through all of these memories, but they're my memories, so I'm hoping they're also interesting for you. So I'll start with undergraduate studies. This is where a lot of you, I think, are. And I'll explain what happened there. So I was only at this school for a year. This is a prestigious engineering mathematics school in Canada. It's well known for putting out computer scientists and engineers. I went there to do engineering. I was kind of pushed there. I was doing all right in high school, as in mathematics and physics, and everyone said, you need to be an engineer. We need engineers, you need to be an engineer. My dad was like, yeah, you need to be an engineer, yeah, if you want to do that. So I was kind of pushed there. I liked the idea, but it wasn't really entirely my decision. I had a great time. I met lots of friends. I had a good social life. However, engineering was not for me, and I didn't do very well. I kind of stopped going to classes after my first semester, and I left the program after 2 semesters. So this was a failure, but I don't really consider it one. It was more an experiment for me. After a year, I decided to go to Newfoundland. This is a smaller university in Canada. So Newfoundland is a smaller place. It's about 500,000 people. Not many people have heard of it. If they ask me where I'm from, I have to explain. It's that island over there on the right-hand side of the map. But it was a lovely university, and I stayed here for a longer time. I went there to actually do English. I decided I'm going to change completely what I want to do. I want to study English, maybe philosophy, and luckily we have a liberal arts type design there, at least at this university. So I could go there without declaring a major, and I could take all sorts of courses. Similar idea to what our liberal arts and sciences program is here. I took philosophy, I took logic, I took some mathematics, I took some computer science, and I took psychology. But what really struck me was the neuroscience. The neuroscience really spoke to me. I thought, wow, this is interesting. A lot of things of what I'm interested about in sciences are here, but also the aspects of English and the humanities are also here. It was a good balance for me. So after a year, that's where I ended up going, behavioral neuroscience. I think it was quite important that I had that choice, however. I would have probably ended up just going again in another direction that I didn't like. I probably maybe went after an English degree and would have had that and then decided this isn't for me. But at some point you have to decide, right? You can't just keep changing your mind. So luckily I had that year to really figure out what was for me. I ended up doing 4 years plus an extra year of honors. So I did a much longer trajectory than I think is common here in Europe and also now in Canada. Things have changed. But at the time I did 5 years of undergraduate, and as I'll explain, another 3 years of master's. So the honors degree itself was what may constitute a master's degree here. I did courses and I actually did a research project. This was my research project. I'll try to explain it. Simple terms. I mean, there's a lot going on here. But what generally I did, we looked at rats, we did animal research. So what behavioral neuroscience tends to look at is animal research. Not my favorite thing, but this is what I did at the time. So we did a thing called Western blotting, and Western blotting is you want to tell whether or not a molecule goes up or down based on some manipulation that you did. We did a manipulation here where we gave an odor and had the rat form a preference towards a part of the cage they were in where that odor was, and we injected them with this thing called isoproterenol. It basically increases their arousal, and what we found was that the concentration went up of a certain molecule. Western blotting here, basically the idea is you have all of these little channels, you put in a tissue, concentrate, and you send electricity through it, and electricity will drive those molecules up based on their molecular weight. And so you can separate out all the different types of molecules. That's what we did here. And then you can, this is fairly rough, it was better in the actual photograph, but you can tell the concentration based on what's going on here. So this is my first real experiment that I've ever done. Hopefully I explained that well enough. I'm not going to go into more detail, but you can ask questions later if you're more interested in what happened there. But this was also my first exposure to the brain system that I'm still interested in. I'm looking at humans now, I've gone on from animal research, but this is the start. So that was my undergraduate experience. So basically, to summarize, I flunked out, took a year off, went back, found my way. That took 6 years. So a lot of you would have already graduated by then and gone on to your career. So I took a lot of extra time to do that. It was kind of a luxury, I realize now, but that's how things were back then, I guess. I'm not sure how the university system has changed in Canada, and I'm not saying this is an easy path for everyone to take. But for me, that's what I needed. All right, I stayed. I basically applied to 6 universities in the United States and never got into any of them. But one of my favorite teachers, Carolyn Harley, was offering a master's position in Newfoundland, so I stayed there. And I'm glad I did. I didn't go to any of these large American universities. I didn't need to. This was a really cool spot to be anyway. So I stayed for an extra 3 years here, in Newfoundland. Again, 3 years is a long time nowadays for a master's program. Here it's either 1 or 2 years. But this allowed me to do a full experiment. Again, this was animal research, and I'll explain as gently as possible what we did here. So this part of the brain, you can see here, this is called the locus ceruleus. It means the blue spot. It just shows up as blue when you look at it in section. This is a rat brain. This little guy here is called the cerebellum. You can see that here as well. What we did is we inserted this really small tube called a cannula, and we used that to inject glutamate. That's a neurotransmitter that activates that region. We basically showed that you needed to pair this activation with some activity somewhere else in the brain called the hippocampus. I won't go into much more detail, but it's an important mechanism of memory and learning. This is what we think underlies how we learn about things. And in particular, this region is important. It's get activated when we are emotional, when we are highly aroused. So if you think about the things that you remember best, it's usually when you're in a situation that's arousing. Something has happened that you didn't expect. Something has happened that is new. These are things that we are probably better off remembering than the boring things that happen in our lives, because they're probably more useful to us to remember these things. So that's the system I looked at way back then. Again, this was animal research, and this was my last animal project. I've decided I don't want to do animal research. It's not fun to do these things to animals, and I've decided I'm going to move on, and I'm going to start working on humans. Not so easy. Yeah, not the same way. We're not doing cannulas in humans. And that's what makes it hard, right? This is not, we don't use humans, and we use animals. Happy to talk about the ethics of that with you guys later, though, if you want. I also got one of my first articles from this. So after 3 years of master's, I actually published an article. The title is a bit unwieldy. Hey, I'm not going to go through every aspect in here. What I just explained to you, I think maybe gives a better summary. It's an important mechanism for learning and memory in animals. We think that the same system is important in humans. Okay. Any questions? Any impressions so far? Okay. What happened next? Well, I went and made a huge leap. So what happened, I got an email out of the blue from this guy. I had never met him before. I had gone to a conference called the Society for Neuroscience. It's the biggest neuroscience conference in the world, to present that master's work I just showed you. I put my resume up on their website because I could do that for free. This guy contacted me, and at first I'm like, what is this? It's hard to believe that this is real, but it was real. I looked him up. He was doing interesting work, and it really seemed to fit with what I wanted to do, and it was on humans, and not all on humans. So as you can see, they're also doing animal work, but they were doing human work and computational work, which I was interested in doing. So this was huge. I got this email. I had to think about it for a month or so, let's say, before I decided, let's just make the leap. I had no real connections at the time in Canada. I had connections, but no relationships or anything holding me down at the time. So I made that leap, and it was a huge one. So basically, the first time I arrived there was the first time I'd ever been in Europe. And now, having seen both worlds, I don't think they're that different, but at the time it was a completely different world. Flying over Germany and seeing the little cities and how they're completely meticulously organized compared to the grids that I'm used to in Canada, it was a big change. I didn't know any German either, except for what I learned from a little CD that I've been playing in my car for a few months. I could ask for chocolate cake, that was about it. I did my PhD here, or as they say in Germany, Doctornaat. However, after about 2 or 3 months in Düsseldorf, my whole lab moved to Nijmegen in the Netherlands, where you probably mostly know because it's fairly close to where we are. And so I ended up right on the German border here, spending most of my time in the Netherlands. So completely, again, by coincidence, I ended up in the Netherlands. Same supervisor, but yeah, most of the time we spent here. I hardly went to Düsseldorf afterwards, except to defend my thesis. Here is my thesis. a lot of German stuff, but at least this title is a little bit more straightforward than the previous ones I showed you. I'll give you a little hint of what kinds of things that I did at that time. So I learned a method of estimating so-called cortical thickness. So I don't know how much people here know about the brain, but there's a sheet in the brain called the cortex, and it's folded over many times. So if you see a picture of the brain, you see this very convoluted surface. There are now computational methods we can use using MRI, magnetic resonance imaging, to estimate how thick the cortex is. And this can tell us things about how it degenerates with age or how it associates with other symptoms or other disorders. I was looking at age, so people who had not had dementia or Alzheimer's disease, but they had natural aging, and many of them had white matter lesions. So white matter is the wiring of the brain, and a lot of them had holes in that wiring, basically. We're looking at here in this graph, which unfortunately isn't the best resolution, 70 years and older, in a certain part of the brain. At the bottom here on the x-axis, we're seeing the white matter lesion volume, how much of that white matter is compromised. And here I'm looking at the thickness in that region, the brain thickness, the cortical thickness. And you can see a very strong relationship here. So the more white matter lesions they have, the more this region is also degenerating. So we're basically trying to relate how the wiring of the brain predicts the thickness of the gray part of the brain, the cortex. So this was my first look at aging, and I'm still now looking at aging. So this is another step towards where I ended up going. I'm looking at aging in humans. I also, at the time, developed a software for visualizing the brain. This is supposed to rotate. It's not really that useful if you look at it in a still motion, but if you turn it around, it becomes a lot more useful. But basically what you have here is a 3D version of the brain that's cut off. And here you have the brain in different sections. So if you pretend you take this part of the brain or this part of the brain and cut it very thinly, this is what it would look like. And I'm highlighting here a specific part of that, of the brain. So I developed this software in order to look, for instance, at that cortical thickness I talked about. So cortical thickness is then a difference. This is the cortex in between these two surfaces. That thin part is the cortex. All of this is white matter. That's the wiring. The wiring is a lot bigger than the actual parts that do the computation because the brain is heavily connected. So a huge part of the brain is just wires connecting it to itself, basically. So this is what the brain looks in different orientations. I also learned techniques to look at brain connectivity using so-called graph theory. So if you take the brain and you look at it as a network, you can do some mathematical analysis on it. Here, what we were showing is a hierarchy in the brain. That basically means we have sensory information coming in through the eyes or the ears or the mouth. In this case, the eyes, this is visual cortex in the macaque monkey, so this is slightly different than the brain I showed you before. This is where the information comes in, and as it gets darker, it's higher and higher processing. So it goes here, it gets processed, it goes higher and higher, and at this point, it's highly processed visual information. You've seen everything in your visual environment, and you've identified it as objects at this point, and you're probably thinking about what you want to do with it, or what your eyes are going to do next. So this was another paper that I published on the basis of this thesis. One crazy story for this is that in the first year of my PhD, my supervisor developed brain cancer. So for the last 3 years, he was living with brain cancer, and he didn't make my thesis defense. He actually passed away a few days afterwards. So for those 3 years, however, he was an excellent supervisor, and he kept coming in and helping us out. So only at the last minute did that brain cancer really take him away. That made things a lot more complicated, especially at the end, trying to get this thesis published at a German university where I didn't even attend very often. But they were very good about it. Okay, PhD years. Let me see where I am in terms of time. Doing all right. So moving on, postdoctoral years. So I've now gone through undergrad, master's, PhD. What did I do next? Well, I talked to the person I learned the cortical thickness algorithm from, and he said, well, why don't you come here and do a postdoc, basically. So all of this stuff happened through emails. I never actually applied for these jobs. I never did interviews. That's also lucky that you don't always get that easily. I don't know how that happened, but it did. So this is how it happened, and I ended up with this group. So this person's name is Alan Evans. He's quite well known as a person who's developed like a population model of the brain for humans. Montreal Neurological Institute is a fairly famous institute. It goes back a long ways. They're one of the pioneering institutes in brain surgery. And they also were one of the first places to discover that the hippocampus, which I talked about earlier, is critical for memory formation. They did that because they had an epilepsy patient where they removed both of his hippocampi on either side of the brain to stop his epilepsy, and then it turned out he could not form new memories anymore. This guy's name was Henry Molaison, but he's known as patient HR. That was done at this institute. My idea was to look at brain connectivity in aging and Alzheimer's disease, so really moving towards what I'm doing now. So what did I do here? Again, a lot of information here. I'm just going to try to distill it. These are brain networks, so all these little nodes in the network are brain regions, and I'm just trying to visualize here how those are connected to each other based on different methods that people have come up with to estimate brain connectivity. So we can't just take the brain and count all the wires and look at it, especially in humans, right? We just can't do that. So we have to find ways to estimate it. Some of those ways are, well, we can use what people have looked at in monkeys. Over the last 40 years, people have studied macaque monkeys and have looked at connectivity in monkeys. And since monkeys are fairly similar to us in anatomy, then they can make an inference that that connectivity looks like ours. And that was that supervisor I talked about, the PhD supervisor, he had developed something for that. Using the cortical thickness, you could also make an estimate of brain connectivity. DWI, that means an estimate of that white matter, all the wires in the brain. fMRI, that's function, that's how the brain is active. These are all ways that people use to look at connectivity, and they all call it connectivity, even though it isn't really connectivity. It's just some kind of number that they get. So our project was basically looking at how well do these actually agree with each other. Do they agree or do they not agree? Generally, they don't agree very well. These two agree fairly well with each other compared to the others, but they didn't really agree that well. So that was the main finding that we had here. It was more of a critical paper. We can't really call all these things connectivity if they mean different things. After those 3 years, I think I said already, for personal reasons, we decided to move back to Europe. And I already had a sort of professional relationship here with a supervisor in Jülich, so close again to the Dutch border. And my partner at the time, who was Dutch, wanted to stay in the Netherlands, so we found a compromise where I would take my grant money that I had already gotten and work here in Jülich for a little while. And after that ran out, they hired me there as well. Here's Jülich. So here's the border. And here's Düsseldorf. And I was living in Aachen and driving here. And for a while, I was living in Haarlem, which is way over there, and driving every week back and forth. And that will be relevant in a second. What did I look at there? Same sort of thing, brain connectivity and meta-analyses. So I developed a website. I've done a lot of different things, and this is one of the things as an academic I really find attractive about the job, is that I could be creative with what I did. I didn't need to keep doing the same thing. So when it came up that we needed a way for the group's findings to be shared, because people kept sending emails saying, can you send us your findings? And then we would send them, and then they would ask for information about them. We basically said, we need a website where they can just download it and get that information, and we don't have to, you can cut out the middleman, basically. So we made this website, and I learned a lot about web development through that. Here, I won't go into lots of details, a lot of info, but it's the same sort of approach that I did before, comparing different connectivity measures and making these really nice brain maps. This is basically showing how well they correspond. So where it's red, they correspond with each other, and where it's gray, they really don't. And finally, I came back to the Netherlands, back to Nijmegen. There was a researcher here who had become a professor, and we wrote an application together and got some funding. So I came back to the Netherlands and back to Radboud University. Things changed here quite a bit, so I'm going to explain this. This hopefully is more intuitive than the crazy brain stuff. This is a highway driving task, and this was inspired by me driving on the Autobahn every week with my Fiat, trying to keep up with the cars going 200 kilometers an hour from behind. So basically what you get there is an adrenaline rush, and that's what drives that locus coeruleus system I was interested in, especially if someone's coming really fast from behind. So this is the rear view mirror, and as you'll see in a second, cars are going to come really fast from behind, and you have to make a decision. When you make that decision, you have this increase in adrenaline, and that can be measured by here. So this is where the person's looking, and the size of the circle is their pupil diameter. Pupil diameter is an indirect way of looking at arousal. So that person's quite aroused right now because a car just went by. I'm just going to let this play through, because right now is when some big thing happens. So they make a choice to go. It was a bad choice. It's very close. And so I developed this task over basically a year, and then I had people run it while I was recording from their brain and also looking at their pupil. So what I'm showing up here, where those blue regions are, that's when they're making that overtake. And in most cases, you see that pupil goes up, so they're being aroused. So it's a good measure. If something bad happens, so you see here, the blue is when something bad happens like that, the pupil goes up more, they get more aroused. So this was something that I want to look at, both because it's interesting in itself, but also because this locus coeruleus region that I've really studied as an undergrad is one of the first regions that shows Alzheimer's disease pathology. And so I want to use this to study Alzheimer's disease. So that's where I'm going now. After this, I applied for a whole bunch of faculty positions. I had a bunch of interviews. I got offered a job, one. But it was at a good place with a really sort of one of the places that invented magnetic resonance imaging, what I showed you earlier. So I was very happy to accept this, and now I was faculty suddenly. Instead of being a postdoc with my own sort of freedom, now I'm faculty, and I need to teach, and I need to write grant proposals, and lots of things changed at this point, both positive and negative. So there's a lot of admin stuff that I was given, and a lot of things that got in the way of me doing research, which is the point, but it's still an adjustment when you get to this. But I managed to do really cool things. So because we had an excellent MRI center, I could use a very high field MRI. High field MRI basically gives you a much better resolution. I'll show you this video, but this is imaging of the locus coeruleus. So finally, I don't need to do this in animals. I can do it in humans who are alive, including myself, and I believe this is me. This blue region here is the locus coeruleus, small little tubes right in the middle of the brain. Well, and all the red stuff here are the blood vessels around it. The reason we're looking at this is we want to be able to look at functional activation of the locus coeruleus, but that gets really biased if you have blood vessels nearby. So we want to make sure that there's no big blood vessels, and there aren't. So there's the closest one here. It's about 3 millimeters away, so we can actually work with that. Another thing we did was, this is functional MRI, so it's looking at activation of the brain over time. You can see that's the same 3 sections of the brain I showed earlier, but you may notice it's moving all over the place. The top one, basically because we all move our heads when we're in the scanner, we can fix that. Usually we have methods to fix that. But even when it's realigned, the region we're interested in is still moving all over the place. This is because we're breathing and swallowing, and lots of things are happening in this part of the brain that are very difficult to align. So this is some of the stuff that I've been working on while I was in Nottingham, trying to make fix those problems, basically. Okay, and finally I came here. Again, for personal reasons. We had a kid. I had a Dutch wife then. She wanted to move home. I wanted to go with her. We wanted to be close to family. And we said, okay, let's look around in the Netherlands. And very luckily, within like 2 months of looking, there was a position offered here, teaching heavy position, that I decided, let's go for that. Had an interview, and that was successful. So we ended up in Tilburg. And the idea is to stay here. So I guess you all know where Tilburg is on the map. Yeah, same sort of thing, research, admin, and grant writing, and a lot of teaching at the moment. But I'm still able to do research, which makes me happy. So what am I doing now? Well, I'm using virtual reality. At least I'm starting to use virtual reality. So we're getting these goggles that are going to have eye trackers in them, so we can still do that eye tracking stuff, but really control the immersive environment that people are in. This is an EEG cap, so we're going to be doing EEG as well. I've already done a bit of this. And again, with the driving simulation, but we've got new versions of it now, which are a bit more realistic, not just fog, as you see here. This screen is an eye tracker that we have as well. So what questions are we asking now? Well, I want to know what goes on in the brain when people make decisions. For example, when driving. When they're making decisions, can we predict the decisions they're making based on what the brain is doing? I also want to know questions like, how does anxiety affect those decisions, and how can we use knowledge of the brain to better understand that? In particular, social anxiety. So we have a grant proposal in at the moment to look at anxiety and how people navigate the world and make decisions, and how people with social anxiety make so-called costly avoidance decision, where they avoid doing things because that are probably beneficial, such as making social connections, because they overestimate the downsides and they underestimate the benefits. And we think that this brain region, locus coeruleus, is also quite important for that. So let's hope that gets funded. But my real strong interest is this locus coeruleus system and how it is important for determining whether a person is on the path towards Alzheimer's disease. So it really is early in life. We see pathology in this region with no other deficits. And we want to know, can we actually find deficits that we currently don't detect using knowledge of this system? If so, yeah, when we could look maybe a decade earlier or even more and determine, yes, this person is going here, how can we actually intervene then and prevent them from going there, or at least slowing that progression? So that would be probably my most favorite research direction, if I can go that way. This is a brand new figure I made. You can see the resolution is a lot better from my undergrad pictures. Things are getting better there. Same software though. These are stages of so-called tau pathology. So tau pathology is the pathology I was talking about that starts in the locus coeruleus. That's here. That's these region that I showed you in the other video. It's where it starts. At stage 0, there's no pathology. This is the age span from 10 to 100 years. So one group looked at postmortem brains of people under 10, all the way people to 100 years old. Thousands of these. And they discovered that only people under 10, only 80% of those don't have any of this pathology. Even 20% of kids under 10 have some of this pathology. In this stage, so you can see mostly it's teenagers and people in their 20s, you already have pathology here, and it's already spread to other parts of the brain. That's for those red regions. In this stage, so this is people in 30s, 40s, early 50s, it's spread now to these two regions. And then this is when people start experiencing symptoms. Then it spreads to that hippocampal region, hippocampus that I talked about, and a surrounding region called entorhinal cortex. But you can see how early this happens. And we don't know why, we don't know if it's important. I mean, if everyone has it, then it's not abnormal. It's kind of like having moles, right? It's more a matter of, is there a point at which we can see that this pathology is spreading, that we could stop it, or we could slow it? All right, and what would we like to do? Well, we want to look at locus coeruleus activity when people are doing tasks, just like the driving tasks I showed you. And we're already going to do this in a sort of early pilot study with older people. And this is a study in MRI looking at activation of locus coeruleus. It's not very specific, but it can be done. And other things we're thinking about doing, well, activities. Getting older people to do activities and stay cognitively and physically active, regardless of their state, and here they are fencing with their walkers. So this is the kind of thing that we think will activate locus coeruleus and keep it going. This here is called vagal nerve stimulation. Vagal nerve is a major nerve that is going basically next to the ear. When you stimulate it, you stimulate locus coeruleus as well. So the idea is that if you can regularly do this, and it's fairly, that's annoying, but there's other versions of it that are less annoying, that you can do this at home, and you can do it regularly. This is another way that you may prevent it. And at the bottom, I'm showing pharmaceuticals. There are all sorts of possible pharmaceuticals that can also be used. Least favorite version, but if it works, it works. All right, finally, we're doing good, I think. Something about what I've learned. First thing, you don't always know ahead of time what subjects you're going to find interesting in university and what career path might suit you best. You just don't always know. Sometimes you just know when you go, but a lot of times you don't. And so you need the ability to explore, in my opinion. There's always going to be a trade-off between following your heart and planning for the future, but I think whatever you're doing, you need to have some satisfaction from it. So if you're taking engineering for the first year and you realize this isn't really for me, I just don't want to go to class and I don't find it interesting, then you can second guess yourself and it's not failure. You can stop and start something else. And sometimes, things come down to blind chance. So you could get an email from out of the blue from someone in Germany that changes your life, for instance. But sometimes it's just luck, and you got to roll with those things that happen. But at the same time, you have to some extent make your own luck. So put that resume out there, like I did. Who knows what's going to happen? Maybe nothing, but maybe something. But if I hadn't put it out there, then I wouldn't have got the email, right? What else have I learned? Well, I'm not giving you advice. I'm basically telling you what I've learned. You can take what works for you and ignore the rest of whatever kind of advice people are giving you. It's always based on their experience, and it works for them, maybe not for you. For instance, it's very difficult, I think, in this environment for you to do 8 years of undergrad and master's. It just doesn't work that way. The funding runs out. You just can't do it, I think. So you have to work within the system that you have. So I would not advise you to just keep doing a year and then quitting and doing something else, and then quitting and doing something else. You can probably do that once and then and then keep moving on. But get used to failing. It's going to happen. Don't let it get you down. Academia and also industry outside of academia, it will be competitive, especially the further you go. But there's always going to be more opportunities. So it sucks and it does happen. But you always got to think, okay, well, let's just move forward. There's going to be more things in the future. And in the same vein, get used to criticism, because you'll be criticized as an academic or in industry or wherever you end up. If you're an academic, you're going to put your first manuscript out there with all your pride in it, and you're going to get reviewers who are just scathing, sometimes real jerks. You can ignore them. Who cares? And even colleagues. I'd say some of them are constructive. Try to take the constructive stuff and say, okay, you're right, this part probably did that wrong, but ignore the rest. Who cares? Life's too short. Learn how to say no if you're overloaded. This is important, especially the further you go. People are going to just keep piling, maybe even with good intentions, piling stuff on your plate. If you keep saying yes, you're going to get burnt out. It's just a matter of time. So learn how to say no. I don't want to do that. I'm not comfortable with doing that. Not a race. It really isn't. Enjoy that student experience and don't just think, I'm going to get to the end of this. go at your own pace and enjoy these years that you have as an undergrad or as a master's student or a PhD. Yeah, I guess some of these are self-evident, but I'm going to say them anyways because I think it's worth saying. When you have to make a choice, and I had this aimed first at master's students, this slide, but I think this is generally, if you're going for a new program or a new position, do you see yourself thriving in that position, or do you feel like maybe you're getting pushed there? Does it work with your personal life? If you have to go to a new city, is that going to cause stress, that you're going to have to travel a lot? You and your partner, if you have a partner, are going to be apart. There's a language issue and you're not comfortable with that. Think about those things. Does it fit in your career plan? Where do you want to go? And again, it's okay to switch. It's also okay to leave academia. Most people, I would say, do. You don't have to think, I need to follow this path because that's how, the traditional academic path is this and this and this. We can't all go that path and we shouldn't. It's normal. Just don't consider any of that failure. And again, within practical limits, right? You can't keep changing your path if, practically speaking, it doesn't work for you, but it's still not failure and it's still okay to do it. Okay, that's it. That's my spiel. Thank you for your attention.
Is there anything you do regret?
Like really regret? Not really. I mean, sometimes I look back and say I shouldn't have gone back to Canada or I shouldn't have come back here. What would have happened? You see how your colleagues are moving in different directions than you. Even taking this job, sometimes I think, well, I knew it was a teaching heavy job, but that really means that my research output has gone down. And some of my colleagues are in research institutes where their research is up. And I thought, well, if I'd have taken that position, maybe I would be there too. But that's not really regret. It's more looking at it as, as a parallel universe I could be living in. But yeah, not really. No real regrets, let's say.
I have a neuroscience question. Can we go back to the slide, one of the last ones with the aging? This one. First question is a clarification question. If I understand it right, that already at the age 10, 80% of people have the pathology?
No, it's the opposite. So 80% are in stage 0. Yeah, it's a bit tricky to follow this.
Yeah.
This is stage 0. Blue means there's no pathology.
Okay.
So in stage 0, 80% of people under 10 are in stage 0, meaning 20% have some. It's been found, maybe 1 or 2 cells. It's not a lot, but it's there, it's present.
And does having the pathology already then a predictor of developing?
No, so we don't know that. They maybe, probably 10 years ago they did the study. All they've done, it's all post-mortem, so you can't follow up, right? Post-mortem means after death, so these people have died and they donated their bodies, and they did the research on them. So you can't see what happened later. Okay. And otherwise, it's very hard to track. So I'm writing a review paper right now trying to say, what other methods do we have to track this? And it's quite hard to track. You can't just do a blood test. They're working on that, but you can't do a blood test, at least at that point. So we don't know. We don't know if it's predictive or not. Could be not. Could just be a coincidence, but we're hoping at least at this point it isn't, so that we can use it to help detect.
So do you hope to look for predictors or methods to look at this?
There would be the same thing, I'm hoping. So methods that can track this will also be predictors. That's what I hope. So if we can look at, let's say we are in this stage now, and we do that in vivo, meaning in life, so in live people, using blood or MRI or other ways, such as the driving task, hopefully, things that are less invasive. Then, if we can see that there are already deficits because they're predicted by this pathology, then that would be a predictor that Alzheimer's will happen. And so then the idea is to find both those predictors and some intervention. And I think the intervention is to activate this region. So a lot of times later in life, people become a bit more sedentary, and that is a predictor of Alzheimer's as well, that they're not as active anymore. They don't take many risks. They don't do things that are challenging or new, and those are all things that activate this region. So this region becomes underactivated, is the theory, and that is what allows that pathology to transfer.
And you hope to follow the subjects longitudinally?
Yeah.
Very nice.
Yeah, we hope to look at them at different time points and then see if we look at them in the first time point, does it predict where they went later in life? Yeah.
Thank you.
Thank you. Yeah.
Thank you. Are you the only one in the world to came so far with this research?
I'm not, no. So, as I said, I'm writing a review paper right now, and I'm just discovering how many people are looking at this from many different angles. So molecular neuroscience, so looking at the cells, just medicine, looking at MRI, things that I'm sort of looking at, but in different ways than I'm looking at them. Lots of doctors are looking at it. So there's a huge wealth of knowledge doing this, looking at this, but not really in this way, and not particularly this system. I have to say, my master's thesis, Carolyn Harley, supervisor who I talked about earlier, who unfortunately passed away 2 years ago, she was really working on this. She was doing animal studies that have really shown when you activate this locus coeruleus region, it moves this pathology in mice, but it's human tau, so it's really indicative that this is driving it. So her recent research has really inspired me to write this review and look at it in humans. But there are at least 5 or 6 groups, mostly based in Europe, who are looking at humans the way I want to do it as well. So it's a hot, active research topic at the moment. Yeah.
Hi, this was very inspirational, and since the day I met neuroscience, I want to become a researcher in that area so that I can say that I want to follow your path. And I was going to ask how I can do that, and what would be your suggestions to a future researcher?
Okay, so where are you now?
I'm just in my first year studying cognitive science and AI.
Okay, great.
Yeah.
So I think you're in the right place. There's a lot of research that moves toward artificial intelligence. That would be more computational, but there's a huge part of neuroscience that's computational, that makes models of the brain or that uses the brain as an inspiration for artificial intelligence. And some people even try to mix the two and say what we've learned about artificial intelligence can inform us about how the brain works. So I would say stay on that path. But yeah, you kind of, at this point, look for things like internships, look really carefully at what you want to do for your thesis, because that will kind of push you in the direction you go afterwards for a master's program. Look already maybe for research master's programs that excite you, interest you, and then that can help guide maybe your course choices if you have those. So hopefully that helps.
Okay, thank you.
Yeah.
Hi. I'm sorry if I remembered this wrong, but I think you said something about predicting our behaviors according to the brain activity. Is that really possible to do?
So what I meant there, hopefully yes, but what I meant there was they've already done the activity. And then I want to see whether I can look at the brain activity and predict what they had done already. So it's not really prediction of behavior in the future.
That's what I said.
Yeah, it's a good question. I mean, yes, to an extent, I think we can. So we can predict maybe 5 seconds before what they're going to do because this locus coeruleus region starts getting more active in preparation for doing something, although we still don't know if they're going to do it. We know that they're more likely to make that decision because the locus coeruleus is saying, oh, I want to do something, but you could still decide not to do it. Well, it's a good point, yeah. So when I say predicting here, I'm just saying it. You take 2 time series and you predict one from the other, but it's not predicting the future.
I read that the decision is made in our brain before we consciously make the decision, no? So it's...
In Mind and Brain, did you hear that?
No. In the books I read about neuroscience.
Yeah.
But so then also not making the decision would be predicted, no?
No, I don't think it would be, no.
Okay.
I don't believe so. I mean, you can still cancel the decision at any point. It's not really made. I mean, yes, there is going to be a discrete amount of time where that decision is made and signals get sent to your muscles. And at that point, those muscles are going to do what you told them to do. So that's still an amount of time, but those are milliseconds.
So are we talking about conscious decisions or reactions?
Both. Conscious decisions even more so, because conscious decisions are ones that you had to think about and deliberate about. So a lot goes into having made that decision, like buying plane tickets is a good example, right? You don't usually just go as a reaction buy plane tickets. You think about, okay, I want to go here, I want to do a holiday, you plan that holiday, then you say, I'm going to go online, I'm going to find out what the best prices are, what the best dates are, then I'm going to go through the whole thing, and finally I'm going to click yes. And it's that clicking yes where people might say, oh, that's a reaction, because you have a button and you click and you have made the choice and you can't go back.
No, but I'm talking about saying, okay, I will click the button before I consciously realize that I decided this. There is a decision in the brain, no? I don't know.
During
I'm
the
asking.
pressing the button thing, yeah. I mean,
Yeah.
there will be, and I think it's a matter of milliseconds though, however, and it's just because it takes time for our body to do things. Even in that time, you could say no and accidentally click. But yeah, I don't buy the... So we had this debate every year in Mind and Brain, which some of you maybe have attended, on free will and whether we have it. Yeah, and I usually take the side of, yes, we have free will, and the experiments that purport to show that you don't are mostly, I mean, they don't find them convincing. There's brain activity that always happens before you click a button. Doesn't mean that you didn't make that choice consciously, that you had no choice but make that button press. But we can go down deeper into the philosophy of that. But we won't here, maybe, unless you want to, but I don't think we have time.
Over drinks.
Over drinks, we can do that, yeah. Sounds good.
Thank you. Hello, I'm studying cultural study here, and I just wonder, is it possible to connect neuroscience study with literature study? Because last semester I was in Aarhus University in Denmark.
Yeah.
There was a music and brain center, and I involved in some experiment like to see MRI and MER function, and when we hear some music and see some pictures. And so because I'm a literature study, I'm a master student and expertise in children's literature. So is it possible to see what's the literature and the words and also pictures to influence children's mind? So
is it possible to what?
To see what the language, literature, and the pictures to when the children accept that, when the children approach that. So, is it possible to learn what is the function in the children's mind?
Is it so? There are studies that have looked at when people are reading or when they're looking at things, what parts of the brain get activated in that sense.
Yeah, because for now the literature methodology is normally from the parts of the words and language and the analyze the text. Mm-hmm. So is it possible to study the literature from other perspective? Sorry.
Yeah, I mean, in terms of, are they reading? Is that what you mean? Yeah. In terms of language, there's a huge field, let's say, of people who look at brain activity during language or look at eye activity. That's quite popular to look at eye tracking, like what I showed there, while people are reading and where their eyes go. Especially you can show then what the difference is between children, let's say, and adults, how they are reading. In terms of brain activity, I think you can also do that, but I'm not familiar with those studies, but you can look at what's happening in the brain while people are reading. If that's what you're asking, I'm not sure.
Thank you.
Yeah.
Thank you.
What sparked the focus on Alzheimer's or dementia in your career?
Good question. Yeah, you might have noticed it was sort of gradual. So I was first interested in just the brain, then this locus coeruleus system, and when I moved to Germany / Nijmegen, it just kind of happened. So there was a researcher there who had a big data set where he'd scanned a bunch of people. He was a neurologist. He scanned his patients. They all had some degree of white matter lesions, and they were all older. And he came to us and said, I need people to analyze this. So we've got a lot of clinicians here, but not a lot of computational people, and we want to figure out how to analyze it. So I learned this brain cortical thickness technique. I applied it to that I found interesting. And I kind of went from there. So aging became interesting for me, and then Alzheimer's was really because I had read this review paper with the postmortem studies. Went back. So my parents lived in Newfoundland, so I went back there all the time for holidays. And my thesis supervisor, Carolyn Harley, lived very close by, so I would visit her. We still stayed in touch. And I told her about this study, and we got really interested in it. She went off and did the animal research, really amazing stuff. And at that point, I thought, okay, this is where I want to go. I want to do Alzheimer's. I want to sort of combine what I learned in my master's with what I've done in my PhD, and it went from there. Yeah, I guess that's it. It was sort of a gradual thing, though. It wasn't just this. So none of my grandparents had Alzheimer's, for instance, so it wasn't really a personal reason at the moment.
Okay, and are those longitudinal studies that you want to do, are they already running, or is that something you're looking for funding for?
No, I need money. So we're doing pilot studies right now. We're looking at healthy elderly individuals. That's going to start in a couple of months. We got a little bit of funding. We're going to do this driving task, but we're not going to record brain activity, just doing the task. And we have a navigation task and a few others. We want to see if these tasks can be sensitive to changes, but the idea is to get more money to turn that into a longitudinal study. So the short answer is there's no money yet, but when there is money, that's what I want to do. Yeah.
Hi.
Hi.
Oh, hello. You mentioned something about the ethics when you changed from testing on animals or running experiments.
Yeah.
Was there a particular experiment that caused that, or was it just something that you felt personally?
Yeah, maybe it was a combination of both, but the first experiment I did was already quite unsettling, especially the first time I did it, because it was rat pups, basically newborn rats without their eyes open. We had to put them in a little cage, and they walked to see where the odor was, and had to watch them do that and record where they went. Then I had to cut their heads off, and they shook all over the place, and then I had to quickly take out their olfactory bulbs and put them in black ice, so to freeze them so that I could do this testing. That was not nice. And the first time I did it, I was sort of just was shocked. Then I got used to doing it. And then I did this other animal study. Also, we had to open up a hole and put in a cannula in two different spots. These are mice that are rats at this point. Rats that really trusted you. So they were now adult rats, but quite tame. They would run all over you. And then you had to do that to them. So after that, I was like, this isn't for me. I love animals too much, I think. I don't know. I really appreciate that animal research is necessary to find out these things. We would not know any of this Alzheimer's stuff without it, but it wasn't for me. That's why.
Yeah, I was going to ask, do you think not testing on animals, if you had continued testing on animals, you could have potentially made more progress as you went, or did you need to move to humans anyway, after discovering that this was something that can occur?
That's a great question. Yes, so I still look at animal research, and especially during this review that I'm writing, and it's so clean, and there's so much you can do. There's so many modern methods and techniques where you can really finely control all the molecular mechanisms. So if I had gone that direction, I think, I would probably be writing some of those papers that they're writing. But they're writing them, and they can't look at humans. So that making that transition to humans is actually quite difficult. And all you can do is guess that what you did with the animals translates to the humans. So actually, I think going in this direction gives me a unique opportunity to make that, because not a lot of people, I think, that do human research had started out with animals. So I can make that bridge, hopefully. But yeah, it's a great question.
Yeah, hi. I wanted to ask more about your career path.
Mm-hmm.
You've painted this global life, path, and I didn't really hear something about the cultural differences and what that brought to you. Would you have the same experience and the same knowledge if you've stayed in Canada? Maybe that's
right. Definitely not culturally. No, I think I've learned a lot about different cultures. It's still European culture. I haven't, gone outside of that bubble, but still, there are quite a lot of differences. And I think, having lived in the Netherlands, having lived in England, having lived in Germany, I can really see those differences and also the similarities. So that, I think, unique. I would never trade that for anything. It was quite. It's quite nice to look back on And I'm here now. I'm married with a Dutch person, and we're raising a kid here, and this is home now. Maybe when I moved here, I never imagined that would happen, but kind of immersed in this culture now. But yeah, in terms of the research, I don't know. I don't think that would have changed a whole lot. It's possible there's some differences in research culture as well, especially in Germany. They're much more hierarchical. So they have, basically people stay in their position for a while and then they bring in people that they like, and it's a much more like a business as opposed to here where there's a lot of resistance against that sort of thing, and in Canada as well. So there are differences there. Also in the granting culture, it's a little bit different. Yeah, so there are differences also academically.
You've been studying neuroscience for a while, right? You've been through, well, we saw the most basic models compared to like the high resolution ones we have right now. So you saw quite some phases over the past years of how research is developing.
Yeah.
What do you think could be a next step in research on, for example, humans in the field of neuroscience?
On humans?
On humans, yeah.
Yeah, so there are a lot of cool techniques coming out. One is MEG, so it's a different version of the EEG cap you saw there, but it's a lot better resolution. Normally, in the last 15 years, it's been you'd have to sit in this big machine like this with a tiny little thing around you and a big, that's because basically it has helium and it super cools and it's necessary. So you can't do much with that. You're sitting back and maybe you can look at a screen and do things. But now they've developed in Nottingham actually these hats you can put on with single sensors, and they're getting more and more of them, where you can actually stand up and move around. So this wearable MEG system, I think, is one of the big exciting changes in measuring brain activity, because you can go deeper and with better resolution. MRI is a similar problem. So MRI, you have to sit, especially that high resolution one I showed you. I've been in there, it's loud and it's really tiny, and it's very claustrophobic, and also when the thing sends its signal, you can feel it sometimes in your muscles. It's not a natural experience, so it's really hard to simulate that natural experience. So if you wanted to study how humans are in their natural environment, it's not the right system for that. So we are getting better systems, I think, for that. So that's one of the major things. For humans, what else do we have? Well, the eye tracking has become popular. VR has become popular. Yeah, I can't think at the moment of anything else, but I'm sure there are more things on the horizon for human research.
Let's give it up for Andrew Reid, everybody.
Thank you.